All right. Let's see if you guys could do this. Remember, okay? Charlie Brown, right here. So that we want you to name it. Why did I start one over here? Well, you got to remember that these molecules are three-dimensional. So this is technically one, and this is technically one because you could spin them. It doesn't matter which side you start with. So you have every point, and this is how they're going to look in college. Every point is a carbon because scientists are lazy and we don't like to do extra work if we don't have to. There's a double bond here, okay? So you have 1, 2, 3. I have a methyl group over here, touched on the third, and it doesn't matter which way you go, 1, 2, 3, right? And we have to name this double bond. So you would have, and this is a really fancy name. It's not how we do it, actually. So 3-methylhexene, and we put the 3 in between here to show where the bond is, or you can go 3-methyl-3-hexene, which is fine. If you got that right, awesome. If not, don't worry about it. All right, so what is an isomer? Well, an isomer is iso, remember, equal. So what is it? Isosceles triangles, and mer just means part. So it's just different chemical formulas for different structures. The thing is with, where are we? We're at organic chemistry. There's just so many isomers. And I would show you the difference if we were in the classroom. I would show you how many in like a book that lists names of organic and inorganic molecules. Organic just quadruples the number of pages in the book. So here's an example of why there's so many isomers, okay? And again, we would say 1-hexyne. We wouldn't put the 1 in the middle, but this is hexyne because it's got a triple bond. Okay? It's got the same number of hydrogens, same number of carbons. It's just where the triple bond moves to. And just by moving the triple bond makes it a totally different compound, and it acts differently. And when you get into college, you're going to learn that there's left and right-handed, for lack of a better word, molecules as well, like glucose, for example. Just like gloves, 2 gloves look exactly alike, but they operate differently chemically. Which prefix did you use? I don't know why we have this. Isomers start off with, it should have been a hex. I might have had an example on the board if we were in the regular classroom. Okay. We're not going to do review questions 1 through 33, but I guess you're doing that for homework. So we're going to skip all this. Which is the correct IUPAC name for the hydrocarbon right here? Well, this is where it gets tricky because this is not a dingle-dangle that dangles off the dongle. Because remember, they're not straight. So it would be 1, 2, 3, 4, 5. What would 5 be? Pent, right? No double or triple bonds. So pentane. I'm asking you to write the structural formula for 3-methylpentane. So you would draw 5 carbons and put a methyl group on the third one. It would look something like this. Okay, 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. And here's your dingle dangle. It dangles off the dongle. Now here's the thing: is you have to take the longest line. So this can't be 1, 2, 3, 4, which would be butane, and say that this is a ethyl group. You can't do that. Okay. Now this is kind of clear because it's straight, but they're not always that clear. How about 2,2-dimethylhexane? Well, you draw your hexane first, right? And 2,2-dimethyl, that means you have 2 methyl groups on the second carbon. And that's what it would look like. Now, again, once you get dingle dangles that dangle off the dongle, you would start numbering from the side which has the closest number of dingle dangles that dangle off the dongle. So this is where this one's really interesting. You have 1, 2, 3, 4, 5, 6. Okay. You could also go this way. 1, 2, 3, 4, 5, 6. So no matter which way you go, it's a hexane. But you wouldn't go that way because you want to go the closest to the end with your dingle dangles. Here's a cool one. 2, 2, 3, trimethyl heptane. So draw your heptane first. 1, 2, 3, 4, 5, 6, 7. It's an ene, so you have no double bonds, right? Or triple bonds. It would look something like this. All right. I want to keep on going. Here's just some more examples. This is what I was going to have the other class do, relative abundance. And we're going to stop there, I think. Or should I just keep going? Let's see. Oh, let's look at halide groups. So halides are just group 17. So you add a halogen to them, okay? So the name of the halo group is fluoro, chloro, bromo, and ido. And a number in the place which indicates where it's attached to the carbon. So if you had 1 chloroethane, you would draw an ethane and then add a chloro to it. If you had 2 bromo butane, then this one here would be 2 fluoro butane. One or more dingle dangles or dingly danglies. Use the following prefix. So if you have 1, there's none, 2 di, 3 tri, 4 tetra, and 5 penta. So for example here, dichloro, draw your butane, and then 2, 3, right? So it doesn't matter which one is 2, 1, 2, 1, 2, it doesn't matter. 1, 4, so 1 is pretty specific, so then this one has to be 4. You can't go this way, you can't say 2, 5. You have to start with the closest one. 2,2-dimethylbutane. Draw your butane. And then you need a methyl and a methyl. I don't know why that one's in there. 1 chloro, 2, 3-dibromo. That's a tough one. So how did dingle dangles get on the dongle to begin with? Well, if you have a hydrocarbon is saturated, like an alkene, you're going to have to watch this video to find out more. We're actually not even going to get into any of this stuff. So I'm going to have to figure out a way to erase this. Okay.